Hello, everybody. Welcome to Calculus 1. We'll be using the OpenStax book, Volume 1 of Calculus, and we'll go right into Chapter 1, which is the review chapter. Hopefully, you will know most of the stuff that will be presented in Chapter 1. So we'll get right into Section 1 of Chapter 1. All right, let's get started. Okay, so Chapter 1 is a basic chapter. And so some of the stuff that I will be talking about would sound like really elementary, but I do hope that you will be able to review these concepts and make sure that you master these before you actually get started with calculus concepts, which will be appearing in Chapter 2, or maybe the last part of Chapter 1. All right, so the first thing we have to study is to understand is the idea of functions. Okay, now, you may say, I know what a function is, right? Let's just talk about what it is. But I do want you to really understand this. And the reason is because mathematics, and in particular calculus, is pretty much all about functions, all right? It's a study of functions. All right, so F is, we write the notation like this. And by the way, also be very attentive or pay close attention to the way I write, because this kind of notation, the mathematical symbols, are universally used, and you do not want to use wrong symbols. All right. So when I write F followed by this colon and then A arrow B, this means something very specific. This means F is a function that takes the elements of set A to set B. We say this is a function. Okay, let's see what this implies. All right, so here we are, like I said, A and B are sets. Now, they don't have to be sets of numbers, but they are just sets of, any objects, which are called elements. A and B are sets, okay? Like the set of real numbers. Now, I should also call your attention to this. When I write this script R or boldface R, that means a set of all real numbers, okay? So anyway, we have the set A. It doesn't have to be all the real numbers, by the way. A and B don't have to be, okay? But here's what it means. For each X in A, so every element of A is associated with a unique value or element in Y. So for each X in A, there is a unique, okay, element in B. All right, so let me write this: unique element Y in B, such that S dot T dot, and I will be using this a lot, such that, okay, Fx is equal to Y, equals to Y. All right, so Y is mapped, or I should say X is mapped to Y. Well, you can say Y is associated with X or something like that. All right, now A is called the domain. And every element of the domain has to be mapped to an element in the set B, which you may have learned this word range, but more broadly, I will just give you another more technical word, which you'll be using later probably in your advanced mathematics classes. We use the word codomain as opposed to the domain. So the elements X, the input values, come from the domain. The output, the result, comes from the set B, which is the set called codomain. And if you take all the images of every element of A, that particular set, which is a subset of B, is called the range. But anyway, I will not worry too much about this. All right, now I will also be using this notation EG. Now, this is a common notation, which stands for some Latin expression. I don't know what that is. Some of you may know what that is, but it means for example, right? So every time I use an example or I present examples, I will be noting or writing EG, okay? And that is to distinguish this from EX, which could stand for, example or exercise or whatever. Okay, so EG means example. All right, what kind of examples? What kind of functions do you know? Right. Later, we'll be talking about all kinds of functions, and we'll try to classify them. So here's a function. This happens to be a linear function. You can also have a square function. You can have a reciprocal function. You can have a logarithmic function like the natural log of x, or a trigonometric function like sine of x or sine of 3x, or tangent of x. Now, by the way, some of these are not defined for every real number. I hope you understand that. For instance, this one is defined for all x, a real number, except for 1, right? Which is one real number, which is 0. All right, now this one is not defined when x is 0 or negative. This is defined for all reals. That's fine. This is not defined for a whole bunch of real numbers, x, such as pi over 2, 3 pi over 2, and so on, right? We will briefly review these things. Okay, but as I said before, x is mapped to y. Okay, this is the idea of the function. And by the way, we don't have to call the input x and output y, but many times that's what we identify with these letters. Okay, x is also called the independent variable because you independently choose these, but then the value y, of course, depends on x. So this is called the dependent variable. All right. Okay. When you try to find this y, we call this evaluate. So evaluate f means finding fx at a particular point. All right. So for instance, I mean, this is really, really simple. But again, if I say evaluate, so f of x is equal to x squared plus 5, right? Evaluate this at 3, for instance, okay? And that's going to be 3 squared plus 5, which is 14, and so on, right? So that should not be too difficult. And I hope you know how to do that, basically. All right, so then that's one thing that we should remember. Now, let's talk about what a graph is. Now, if I ask you to graph this function, I think you can do that. For instance, let's graph this particular function, right? Evaluate this at 3. This is what you did. Graph it. Well, so when you graph these things, okay, we have to first figure out, okay, f of 0 is equal to 5. Let's say this is 5, 0, 5. Okay, and then when x is equal to 1, so this will be 6. And when x is equal to 2, that's going to be 2 squared plus 5, that's 9, and so on. And then you can do the same thing with the negative values. And you can see that this is going to be a parabola, which you should be quite familiar with, right? But let's stop and think about what we mean by a graph. A graph is what? It's a visual representation of the function, of course, right? But the graph, here's a technical definition, or more precise definition of the graph. Graph of f is basically the set of points. What points are they? Well, the first coordinate is x, and the second coordinate is y, which is fx, right? And so that is what we call the graph of f. What I do want you to realize here, especially, is that when we say a graph, okay, we mean the set of points on xy plane, where x is the input or the independent variable, and y is the dependent variable. Okay, so let's continue. Okay, so I have shown you various ways to represent functions, right? So you can write a formula. You can also do, like an XY chart. You can do graphs. You can also do this diagram, like this. A, which is real numbers. B, which is also real numbers. See, this function, this particular function, happens to be the set is a function from the reals to the reals, or the set of real numbers to a set of real numbers. So when I plug in 0 here, for instance, you get 5. When I get 1, you get 6. And of course, when you put -1, that also gives you the value 6, and so on. When you put 3 for x, then 14, and of course, you can continue. Okay. But the problem, of course, with this kind of representation is you have to write all kinds of numbers, and you may not have enough space. Okay, it's a lot easier and more compact if you describe the function by its formula. Okay, just like this one here. Graph is, of course, very helpful. And what I want you to know, and by the way, something interesting is happening here, right? Two different elements of x, or of the domain, are mapped to the same value in y, the image. And so this is telling you something very important about this function, namely not one-to-one. That's something we'll come back later, I think, in section 4 or section 5 of this chapter. All right, but in essence, okay, this is really a helpful picture, and I will be referring to this more and more, I guess. X is the input, and that gets into this box. So think of any function as a box that is programmed to do a certain thing, one specific thing, right? So when you put x into this box f, this particular box f, okay, what f does is to take what you put in, squares it, and add 5 to it. And what comes out is the input, which you can call y. You can denote that also as f of x. And in this case, it's the input squared plus 5. All right, so this particular function is programmed to take the input, square it, and add 5 to it. All right, so that's what we do. All right, so that is the first idea of section 1. All right, so maybe I should go back and say, this is the very first thing we do. Understand the most basic concept, or the elementary concept of what a function is. All right, number 2. Now, this is also something that you should be familiar with, but it's interval notation. Now, I mentioned a few minutes ago that many times we'll be talking about domains and ranges, and these are usually the set of real numbers. Okay, so what is a real number? And here's the answer. Well, actually, it's very, very hard to define what a real number is mathematically or rigorously. Okay, so think of the number line, and every point pretty much represents a real number. All right, so for instance, you have 0, 1, 2, 3. Numbers like 1, 2, and 3 are called what? Natural numbers, right? Some people include 0, some people do not. These are whole numbers, and then if you put -1, -2, and include all of these, that's called integers, right? And then I'm not going to go into all the details of this, but then you have fractions, like right here is 1/2, you know, there's 1/3, there's 2/3, and so on. If you put all the rational numbers, or the fractions of integers over integers, you will see all the rational numbers, and they seem to pretty much fill up the space, but the line, but it doesn't. Okay, and in fact, the set of rational numbers is so much smaller than the set of reals that well, it's incredibly smaller. Okay, but anyway, you had numbers like pi is right here, right? And then there's a new number that you may learn, or you may have learned already, called e, and the square root of 2 is somewhere around here. Okay, these are called irrational numbers, right? So if you put all the irrational numbers and rational numbers, and by the way, all of these can be written as a decimal, either a terminating decimal or repeating decimal, or non-repeating, non-terminating decimals, which are irrational numbers. All right, so that completes the real number system, which is this R. This is the set of all real numbers. Okay. Now you can also write this, and this is exactly the same as the interval from -infinity to +infinity. Because, oh, by the way, infinity, I should mention, very important. Infinity, this may come as a surprise to some of you. Infinity is not a number, okay? When I say a number, or when when mathematicians speak of a number, we're talking about some finite quantity, typically. Actually, numbers are also very hard to define. Maybe that's a question in philosophy. But anyway, when we talk about a number, we're talking about one specific, real number, perhaps complex number, if you include I and its its relatives. All right, but the point is, infinity is this concept which is bigger than any real number. So this is called potential infinity. And just remember that infinity is not a number. It's something that you do want to remember. So you can't, for instance, write anything like this, let x be infinity, right? This is really bad. You can say, as we do later in chapter 2, we can say x approaches infinity. That means x gets bigger and bigger without bounds. All right, so this is the first notation, the interval notation. All right, so along with this, we can also talk about these different intervals. If you have a particular point A and another particular point B, let's say B is bigger than A as indicated by this picture, right? We write this, by the way, this is a set of all x such that x is, or A is less than x, which is less than B. Right? This set, subset of the real number set, is denoted with A, B, like this. And this is an open set. It does not include an A, the A or B. Okay. Now, if you do include both of these, this is a set of X, which is such that A is less than or equal to X, which is less than or equal to B. And we denote this with square brackets. And this is called closed set. A closed set includes the boundary points. And the words open and closed, it's sort of easy for us to just, to say, well, open just means that the points are not included, the endpoints are not included. Closed sets mean that the endpoints are included. And that's fine, for you to understand it this way. But it turns out the words open and closed are extremely important and technical, okay, in the mathematical field called topology. And so these are very highly sophisticated words. So even though the words like open and close seem simple, just remember that there is something much deeper than this. All right, now you could also have half open and half closed, for instance, something like this. And so this can be denoted, well, this means the set of all x, so that x is, or A is less than or equal to x, which is strictly less than B, right? And so this can be denoted with A, B, where the A is included, but B is not. So you can call this a half open set or half closed set, or you can say it's neither open nor closed, right? And so, and you can, do lots of different things with this. So for instance, when you talk about something like anything bigger than A, okay, so this will be the set of x that such that x is, let's say, bigger than or equal to A, right? So this is like, it goes to infinity, right? So you can denote this way, A to infinity. Now, you never want to have a square bracket nearby infinity, just because infinity is not a number and it will not be included in any interval, right? Okay, and then you have other variations. We will not go into those things, right? So when we say find the domain, or sometimes a range, you say find the domain for something, right? So f of x, let's say, is x cubed or something, okay? Is there any x that you cannot evaluate the cube for? Is x cubed defined for every real number? And the answer is yes. So the domain, in this case, is the set of all reals. You can use interval notation like this. You can also just write R if you want. Okay. How about the log? This is a common log of x or natural log, it doesn't matter. Okay, what's the domain for this function? Well, it turns out it's from 0 to infinity. It's a set of positive real numbers, okay, not negative, not 0. Okay, how about this? When you say the square root of x, right? The domain is, well, it could include 0 this time because the square root of 0 is actually 0, and then go to infinity, right? So that's how you can write these things. Oh yeah, by the way, what happens if you have 1 over x plus 3 or something? Okay, so this means, okay, x can be anything. Okay, so x can be anything, any real, except -3, right? Okay, so you could say x is not equal to -3. That's one way to write that. You could also use a interval notation like this one, -infinity to -3. That's okay, as long as you don't include -3. And you can have any number between 3 and infinity. Okay, so this is, what is this saying? This is a union. It means either here or here is okay, which is basically, I mean, this is, you know, come on. What is this saying? This is a nice way of saying, look, if you are -3, oh, sorry, this is -3. If you're -3, you are not welcome, but everybody else is welcome. Okay, so this is sort of a polite way to say, we are going to exclude -3 and only -3 from the set of real numbers. Okay, all right, so that is what we write. Okay, all right, so we will pause here, and then we will cover the second part of chapter 1, section 1 in the next clip. All right.